Welcome to GameStack Live. My name is Mike Sterling, and I'm a program manager on the Gaming Experiences and Platform team here at Microsoft. Today's GameStack Live session is Xbox Velocity Architecture, faster game asset streaming and minimal load times for games of any size. During today's session, we will first start with an introduction to the concepts that make up the Xbox Velocity Architecture. We'll view a demo, and then lastly, a call to action. Existing technology has significant bottlenecks when looking at running games on the Xbox One family of consoles. First of all, the read speeds of hard drives don't scale. Hard drives cap out at about 120 megabytes per second of read speeds in optimal conditions for gameplay. With the move to more flash-based memory solutions, those read speeds are increased by an order of magnitude. That is why we have seen the industry move towards more flash-based solutions such as SSDs. Additionally, there's a significant CPU dependency. Issuing the read calls, waiting for data, decompressing, and closing the handles all through the Win32 instruction set reduce the amount of CPU cycles available to a game. This is because of the built-in inefficiencies of the Win32 command set when working with much larger modern titles. And these issues impact all areas of gameplay. When you look at how traditional games are developed, games are broken up into a series of assets. Those assets can be something as simple as a texture that is placed on a box, or it could be something more extreme, like an AI for somebody that you're going to be following around in the game. Those chunks are then loaded into the game as needed. However, as I mentioned earlier, the traditional load speed of hard drives has severely reduced the amount of time that users are actually able to play because you actually spend more time loading those assets. I've lost track of the number of times where I've started a game and I've had to wait a minute to get to the loading screen, and then another minute after I actually start the game before I can actually interact with it. We want to be able to get users into the games quicker. So that's what led us to the development of the Xbox Velocity architecture. As games continue to increase in complexity with these rich, immersive graphical and audio experiences, there were really three things that we wanted to address. First of all, as I mentioned earlier, we wanted to minimize the amount of time being spent on loading screens. Secondly, we wanted to enable a longer or larger draw distance. Imagine being able to see across the map while you're playing Halo. Lastly, as we have seen, more games are becoming open world. Open world games provide a unique set of challenges, and the main issue that we wanted to address with the Xbox Velocity architecture was being able to quickly travel between two different regions without having textures pop in. We want to maintain that immersiveness. So the Xbox Velocity architecture consists of four components: the SSD, DirectStorage, hardware decompression, and sampler feedback streaming. The SSD that's included within the Xbox series of consoles, both the Xbox Series S as well as the Xbox Series X, is a high-performance PCIe Gen 4 NVMe SSD. We worked very closely with our suppliers to develop custom firmware that is designed specifically for Microsoft and the Xbox. This firmware allows us to guarantee 2 gigabytes per second of read bandwidth coming from the SSD. Now, 2 gigabytes of data coming off the SSD is nice, but that data is generally compressed. Another feature of the Xbox Velocity architecture is native hardware decompression. While we did have hardware decompression in previous generations of consoles, the hardware decompression that is enabled within the Xbox series of consoles is integrated directly into the processor. This saves CPU cycles, allows for closer integration with additional features in the OS, and using DirectStorage, it can decompress content directly into memory. The hardware decompression block includes support for both BCPAC, which is a Microsoft standard for texture compression, as well as zlib using the RFC 1950 standard. I mentioned DirectStorage. DirectStorage is a new feature that we developed specifically for the Xbox series of consoles, and it works hand in hand with hardware decompression to provide direct access to content coming off the SSD. This bypasses the entire Win32 I/O stack and allows for direct access to the underlying device. This is important because of the amount of overhead that comes with the Win32 I/O stack, as I mentioned earlier. Especially when paired with sampler feedback streaming, the drive needs to be able to read data as quickly as possible to remove any sort of texture pop-in or bottlenecking. I mentioned sampler feedback streaming on the last slide. So sampler feedback streaming is also known as partial residency of textures in Direct3D. It's also known as tiled resources or reserved resources. However, up until now, it's seen very limited adoption in the marketplace because of the speed of storage not being able to keep up. So, with sampler feedback streaming, we designed the feature to instrument shaders to identify what is visible within a player's field of view and only load in the textures that are necessary for that field of view. That gives us a leap in efficiency, and it allows us to dedicate more resources that would otherwise be used for the rendering of those resources. You could then use those additional CPU, disk, and graphics resources to provide more experiences to your users. Let's take a look at how you can use game asset streaming.
The scene you're looking at was built to a very high level of detail so that the objects can be inspected up close. Over 10 gigabytes of texture content are present in the scene, and we use texture streaming to hold only some of that content in memory at any given time. A traditional texture streaming engine decides to load texture MIP levels using a coarse measurement of which objects are visible and how large they appear on screen. These measurements can be inaccurate, leading to over or under streaming. This memory size is known as a texture budget, and in most titles, the texture budget is the largest single user of title memory and the largest single user of storage. We can estimate what an optimized Generation 9 traditional texture streaming engine would need to have in memory to render what you're seeing right now. It's still a conservative estimate, by the way. Most game engines would likely use somewhat more memory than you see here due to overstreaming. But with sampler feedback streaming, we can use significantly less memory to render the same scene, and a corresponding reduction in the amount of storage we use to load the data into memory. That means that for the same scene, we're loading it faster on Xbox and using less memory than on competing platforms. We think of this efficiency gain as a multiplier on our storage performance and our graphics memory size. With this view of the scene, the value is 3.0, and you'll see the value change as I move around the scene. I should also mention the absolute numbers you see in the memory bars here. They aren't all that high, especially compared to the 10 or 16 gigabytes of memory in our consoles. Our content in this tech demo is fairly simple. A real AAA title would likely have significantly more complex materials and more objects visible. Crucially, however, the comparison between sampler feedback streaming and traditional MIP streaming holds true regardless of material complexity. The numbers will scale with content, and the multiplier will still ring true. Let's compare a Generation 8 traditional streaming engine on a hard drive to sampler feedback streaming running with the Xbox Velocity architecture. I'll start the scene reload now. This camera angle consists of over 2 gigabytes of texture data and simulating a hard drive from the Xbox One X console. It'll take a while to reload all of the data needed to render this scene with its ideal level of texture detail. From talking with title developers, we know that texture streaming is as much art as it is science. Various techniques are used to estimate scene visibility and size for each object, and then calculate how much texture detail must be loaded for each object to make the scene look great. Most titles do complex offline processing to make these estimates better. Some titles show a load screen while textures are streaming. And even after all of this engineering work is done, artists usually need to manually adjust some objects and textures to fine-tune the results. It works, but it's a lot of work. After about 22 seconds on a simulated Xbox One X console, we're done loading. Now, we reload the same scene using sampler feedback streaming from our solid-state drive. It takes less than a quarter of a second. If you missed it, let me replay it for you. Sampler feedback uses the GPU to automatically determine the exact set of texture data needed to render the scene with the ideal level of detail. Our solid-state drive, hardware decompression block, and optimized DirectStorage API gets that texture data into memory extremely quickly. The Xbox Velocity architecture gets you into the game quicker. The game spends less time loading data that it doesn't need for that first frame of action. Additionally, you can see that I can fly around this scene and the system easily keeps up. Thanks to the efficiency of the Xbox Velocity architecture, you rarely see pop-in artifacts. When you're playing a game, sampler feedback streaming allows you to move quicker through the world with higher detail. And since everything loads so quickly, game developers don't have to use twisted hallways between areas or loading screens to cover up texture streaming. There is a ton of detail in this scene. When you get close to the drawings, you can see the texture of the paper as well as even the pencil strokes. And you can see how the memory usage changes as I look at different parts of the scene. You'll note that the memory bars in the upper right-hand corner consist of both a light region and a dark region. The light region represents the amount of memory seen in the previous frame, while the darker region represents the amount of memory that is loaded but was not used in the previous frame. The streaming system is constantly unloading memory that hasn't been needed for a few seconds, so you can see here that as I move, and if I stop, the darker region soon shrinks to almost zero. I can even do quick camera cuts, which are difficult for most texture streaming systems to handle. Each time I perform a quick camera cut, over a gigabyte of new texture data can come into view. Thanks to sampler feedback streaming, only a fraction of that data needs to be loaded. Some games have to have a lengthy load screen, transition effect, or some sort of contrived gameplay element to hide the texture pop-in from a quick camera cut. This tech demo doesn't have any of those tricks. Sampler feedback streaming is really that fast. Earlier, I talked about loading texture pieces, I talked about loading textures piece by piece. Let's look at this drawing on the table. I've switched the scene rendering to color code the amount of detail used at each location. The colors are in rainbow order, from red representing the most detail to purple representing the least amount of detail. On the left is a visualization of which memory is loaded for the texture we're focusing on. Each texture in the game is implemented with multiple levels of detail called MIP levels. The largest MIP level, known as MIP 0, has the most amount of detail, and each successive MIP level has half the dimensions of the previous. The index of each MIP level corresponds to the color coding you see here. MIP levels are used to increase performance as well as improve image quality when objects are drawn far away from the camera. First, I'll show what traditional texture streaming does as I approach the drawing. Entire MIP levels are loaded into memory regardless of what piece of the image I'm looking at. And as I back away, the texture streaming system can choose to unload the more detailed MIP levels when they're no longer needed. Note that these MIP 0 images are rather large, 16 megabytes or larger across most of the textures in this scene. Even with a solid-state drive, it is a consequential decision to load 16 megabytes just to see detail for one texture on one object. Considering the number of texture layers on each object and the number of objects you can see at once, these high-detail MIP levels can really add up. With sampler feedback streaming, however, the system can load these MIP levels bit by bit. It's more responsive because it very quickly loads the detail only where it's needed. It's more efficient because it doesn't load the detail where part of the drawing is off camera. Think about standing next to a building or a statue in a game. You want to look at part of it up close. Sampler feedback streaming allows you to see incredible detail up close, like the placard on a statue, or the face on this drawing. And it doesn't waste time or memory loading unnecessary detail far away from the camera or off screen. With sampler feedback streaming, games can add more detail to every object, large and small, and not have to worry about compromising their entire texture budget elsewhere to make it work. Next, we'll look at this globe hanging from the ceiling. Sampler feedback streaming uses data from the GPU to stream in only the visible parts of objects. In this camera angle, the Pacific Ocean on the other side of the globe is not loaded in yet. However, as I spin around the object, the streaming system quickly loads in the newly visible parts and unloads the parts that are no longer visible. Think about an in-game cinematic when you see a character's face up close. Sampler feedback streaming allows that character to have incredible detail loaded extremely quickly and not waste time loading detail on the other side of the character you can't see. Now I'd like to show you how our sampler feedback hardware feature works. I've re-enabled scene color coding and I focused in on this drawing on the easel. On the left is a visualization of sampler feedback data for this one texture. Sampler feedback is configured per texture, and we are looking at just one of the 475 textures in this scene that are all producing feedback. The texture is divided into regions, and the developer chooses the size of the regions. For each region, the GPU computes the ideal level of detail used to sample the texture within that region. As I approach and pull back from the drawing, you'll see regions of feedback show higher and higher levels of detail, and then you'll see gray. Gray represents no feedback. That's because those regions are now off screen. You may also see some random flickering in the sampler feedback data. This is because we're capturing only a fraction of the sampler feedback data. The GPU is capable of providing an enormous volume of sampler feedback data, and we can carefully tune the level of output to best balance accuracy and performance. We have found that we can discard over 99% of the raw data and still get great results. Game developers have lots of ways to control the precision and amount of data coming from sampler feedback. Each title can tune sampler feedback to best suit their needs.
Now that you've seen the benefits of the Xbox Velocity architecture, you can see why we're so excited about it. We encourage all developers to adopt the usage of the Xbox Velocity architecture for rich, immersive experiences on both the Xbox Series X and the Xbox Series S consoles. The usage of DirectStorage and the hardware decompression functionality allows you to quickly read the data and make it available, while using sampler feedback for streaming to only load the assets that are needed for what's in the player's field of view. For more information on game asset streaming, at GameStack Live, we have 2 sessions. We have a Getting Started with DirectStorage session, which focuses on DirectStorage for Xbox. Additionally, we have a session on DirectStorage for PC, which uses similar concepts, but the feature is still in development. If you are an Xbox developer, there are more details available on the Xbox Velocity architecture and the Xbox documentation, and you could also follow up with your developer account manager for more information. Thank you for attending today's session on the Xbox Velocity architecture and game asset streaming.